All right. So in this section, I wanted to go over some sort of advances in TEM. And so some of these are newer than others, um, but these are things that have been kind of built on the basic TEM that have given us additional usability and features and so forth. So one of the biggest advancements or differences to TEM is something that we call scanning TEM or STEM. And so as it kind of sounds here, we're putting the scanning name on there, and so that sounds like SEM, and it's very similar to that. However, um, it does rely on the scanning of a beam like SEM, but we're still transmitting through. So it actually gives us basically kind of advantages of both SEM and TEM. So what it gives us is that it tends to give us it tends to be great for what we call Z contrast or atomic number difference imaging, and it's also very useful for spectroscopy like EELS, electron loss spectroscopy, and EDS, which we've talked about, and it can be collected simultaneously to imaging. So it's particularly useful when we have small beam sizes associated with field emission guns or FEG, and we can talk about aberration correction, but when we have a very small beam size. So it gives us a lot of useful information, but it's basically TEM, but we have a scanning mode in those cases. All right. So the spatial resolution we talked about in the intro to TEM, that it's very good. However, those advancements are due to advancements in aberration correction. So the resolution, excuse me, is limited by both spherical and chromatic aberrations. And so those are what we talked about in optical microscopy. So unlike light microscopy, where the wavelength limits our resolution, here those aberrations limit our resolution. And so if we're looking at the kind of a typical 100 to 300 keV TEM, the spatial resolution is limited to 2 to 3 picometers. So that's very, very small. So that's something to keep in mind, is that we haven't reached that potential of TEM. And so those spherical and chromatic aberrations, which we've talked about before, the definition of them, the correction of those is what has given us the advancement. And so this plot here just kind of shows resolution as a function of the year, and basically TEM is the red. And so that's kind of the introduction of TEM, and then a lot of these advancements, particularly the green ones here, are from the corrections to TEM. And so with this, we need additional lenses and so forth to do that. So this is an example of an aberration corrected, or AC TEM, which is the terminology that we talked about here. And so these aberration corrected microscopes, as you might imagine, correct for those aberrations, and therefore increase our resolution by decreasing that size, that spatial size. And if you're wondering why these things are so tall, and I told you at the throughout this that kind of TEMs are kind of tall because of those camera lengths, but aberration corrected are even taller because we have an additional lenses that compensate for these aberrations. And so that greatly increases the complexity. The height is kind of a minor effect there, but it also greatly affects the cost, as you might imagine. And so this is one way that we've gotten to those really dramatic improvements in the resolution in the images that you've seen throughout the lectures here.